We're going to introduce a special type of function called the exponential function, and it has a wide variety of applications in the real world. Anything that tends to grow naturally or decay naturally is normally associated with these types of functions. So let me introduce it in a kind of a general way. If I write y equal to b to the x, and I want b as a constant number and x is the exponent. So this is sort of a turnaround from what you're used to seeing, where x is the base and there's a number up here, like x to the second power, for example. So now we're going to put x up there in the exponent and fix the base to a constant number. This is sort of our prototype of a simple exponential function. But I need some restrictions here. I also need to restrict b so that it is positive. And because you open a real can of worms if you have a negative number raised to any power you wanted to. For example, what would be negative 3 raised to the square root of 2 power? That would be kind of hard to deal with. There are ways to deal with those, but they're far beyond our course. And we also want to make this restriction that b cannot equal to 1. You can see that if b was 1, x1 to the x power would just simply be 1, so it would be a constant function, y equals to 1. So alright, so this number is positive and is not equal to 1. So this is what I call a simple exponential function. Okay, I'm going to introduce these by graphing a couple of them. And it's through drawing a graph of these that you get a sense of how they behave and what they might be applied towards. And so I'm going to start with kind of a simple one, y equals 2 to the x power, which is the one I really like to use all the time when I introduce this, because it's pretty easy to follow, 2 raised to a power. So I'm going to let b be equal to 2. And then we're going to explore that function and see what happens. So y equals to 2 to the x power. Alright, what do we do with it? Well, I'm going to form a chart, an xy chart, and plug in some numbers. So for example, if x is 1, then y would be 2 to the first power. That would be 2. If x was 2, then y would be 2 to the second power, or 4. If x was 3, this would be 2 to the third power, or 8. And you see what's happening here. Every time I increase x, what happens to y? Y increases by a power factor of 2. In other words, it gets doubled. So y equals 2 to the x. As I increase the x's by single numbers, by 1s, the y values double. They double. And so you can imagine that these are going to get pretty big pretty fast. And in fact, by the time we get down to 10, we're already over 1,000 here. And by the time we get down to 20, we're over, well over 1 million. So let's go backwards and plot some other numbers. What if x was 0? What is 2 to the 0 power? A lot of people just say, oh, that's 0. But no, think about that. If 0 is up here and I was looking up the scale, I would go from 4, 16, 3, 8, 2, 4, 1, 2. As I move up, I'm taking half. So if I go up to 0, half of 2 would be 1. This is 1. So you may recall this as an exponent rule. Any number raised to the 0 power is supposed to be 1, and there is an exception to that. 0 to the 0 power would be an undefined quantity, but a number raised to the 0 power otherwise is going to equal to 1. And if I go down, what's below 0, the next integer would be minus 1. So I have minus 1, 2 to the minus 1. It's going to be 1/2. And 2 to the minus 2 is going to be 1/4. And I hope this shows up. Yes, it looks like it shows up. 2 to the minus 3 is going to be 1/8. So what's happening, and I didn't write my 1/8 very clearly there, but it's a 1/8. What's happening as I move down here is I reduce the x values by a single digit, then I'm multiplying by a half. So if you were to reorganize this in order, you would see that this whole chart is very consistent. When I move up by 1 on the x, I double the y values. If I go down by 1, I take half of the previous y value. Alright, so you can see then that if we continue to go down the negative range, go down to -4, -5, -6, I'm going to get smaller and smaller fractions. I mean, this is 1/2 to the third power, 1/2 to the fourth, 1/2 to the fifth, and I'm going to get very, very tiny fractions. So it's kind of interesting to see how all this plays out on the graph. And so let's go ahead and plot these points out. And here we go. Well, I ran out of room for on the left, but this will work. Now let's see, I need to go up to probably at least 8. Let's see, 1, 2, 3, 4, 6, 7, 8. I don't think I'm going to get up to 16 on this graph. And I'm not inclined to write all those numbers in. But if we plot these points, 1, 2, 1, 2 is right here. 2, 4, over 2 up 4. And if we plot out the rest of them, you'll start to see a very regular pattern emerge here. It's not a straight line, obviously. In fact, it appears to roll upwards like this. But on the left side, it's going to flatten out, isn't it? Because we observed that, if I continue to go down in the negative range here with the x's, I'm just going to create smaller and smaller fractions. They're still positive fractions. It doesn't matter that the exponent is negative. When your base is positive, then your result is positive. So I'm going to get smaller and smaller fractions as I move left. It's going to flatten out. And we call that, that behavior, we call that asymptotic. I'm going to write that word up. But we represent an asymptote. Alright, so let me write that word in there. A-S-Y-M-P-T-O-T-E. Asymptote. Asymptote is how that's pronounced. So I think we don't pronounce the P, just asymptote. An asymptote is a line on a graph, and a graph will converge to the line. It will blend into it. Okay, and this behavior is called asymptotic. So sometimes you hear that word in your travels, or reading things. You might see the word asymptotic in some literature you're reading. It's kind of rare to see it, but I've seen it up here. So now you know what asymptotic behavior is. It's a limiting or blending behavior. Now what's happening on the right side? This thing just takes off. It just goes up to the sky. So because it's increasing as we go left to right, we call that behavior, we call that exponential growth. So let me write this function as y equals to 2 to the x, and it's an example of exponential growth. Now, many things in life grow exponentially. The most common are populations. When a population has nothing to check it, as far as prevent it from expanding, then populations tend to grow exponentially. If we're talking humans, bugs, germs, viruses, rabbits, you name it. If there's nothing to prevent the population from expanding, it follows an exponential growth pattern. And so now, if you catch a virus, and this is an example I like to use, if you catch a virus, maybe one virus invades your body, And viruses are so small, we can't see them with ordinary microscopes. They are that tiny. They have to be detected by an extremely powerful microscope. But a virus is just it's not either plant or animal. It's just a thing. I'm not sure scientists know if they're actually alive or not, but they in some conventional sense. But a virus will periodically replicate itself. It'll shoot out some material that will turn into a similar virus. And it does this at regular time intervals. So let's pretend that you catch a virus, and that this particular virus replicates once every hour. So on the hour, we'll say, it divides itself. So when you start off at hour 0, you've got 1 virus. After the first hour, you've got 2. After 2 hours, you've got 4 viruses, and so on. And so that would model the population growth of viruses in your body. Now, viruses are so tiny, you need some trillions of them in order to notice them. So after a day or so, this gets so big, it's now into, we'll say, the trillions, and now your body starts to notice these viruses. They're starting to take over, and at that point, your body immune system kicks in and starts to deal with or fight the virus, and hopefully the body wins. But there are a few viruses that are particularly bad, like the Ebola virus. I think it's about the worst. It has a 90% fatality rate. It's a terrible virus, and it grows so fast that the body can't keep up and fight it. So not too many people survive it. Most of the time we do. But at some point, the immune system will normally kick in, and that will halt the exponential growth. Okay? Insects would grow exponentially if they had an unlimited food supply and no predators. Same with any animals. And sometimes when a new plant or new animal is introduced into a different environment, for example, Japanese beetles or the kudzu vine, or let's see, there's mosquitoes were accidentally introduced into Hawaii around 1826. Without natural predators and a very abundant food supply for those plants or animals, they just start growing exponentially until at some point something has to stop it. All right, so exponential growth, again, I guess to belabor the point, it models growth. Actually, the population of the United States is growing faster than exponential. If you go back to 1790, our first census, and plot it out, it's actually faster than exponential, the way our country has grown, because we've had a lot of immigrants, and our lifespans have gotten much older. And so even this would not be sufficient to model the growth of the United States. But anyway, there's an example of exponential growth. Now, I want to also give you the flip side of this, what's called exponential decay. So I'm going to, I want to keep this graph up here because I like to use them as comparisons. But I'm going to change my function to 1/2 to the x power. So let's see, 1/2 raised to the x power. And if we do that chart, and this time I think I'll start at -3. 1/2 raised to the -3 would be 2 to the +3, which would be 8. 1/2 to the -2 would be 2 to the +2, which would be 4. -1 will give you 2. 0 would give you 1. So without going through and calculating all these, if you plug in 1/2 to the first power is 1/2. If I plug in 2, 1/2 to the second is 1/4. Anyway, I trust that you'll see the pattern here, and I think I probably have this in my book as well. So I'm going to check my book here. Excuse me a moment. Oh yeah, all this is in there, and but it is kind of nice to see it unfold before your very eyes and ears. All right, so let's plot out this one. And negative 3 plots out at 8. So negative 3 comma 8. And then 4, 2, 1, 1/2, 1/4, 1/8, 1/16. So this graph comes down here, and we say it's decreasing because as you move left to right, it's getting smaller in the y direction. So you notice that on the right, it has asymptotic behavior. There's an asymptote here. And on the left, it goes up. But because it's falling, we call that exponential decay. So y equals to 1/2 to the x power is an example of exponential decay. Now, we can make a little adjustment here in how we write this function. I want you to see this. Since 1/2 is the same as 2 to the minus 1, then y equals to 1/2 to the x power would be 2 to the minus 1 to the x power. And then if I remove the parentheses, we multiply exponents. So this would be y equals to 2 to the negative x. So we can also write this function as 2 to the minus x. So here you get a sense that if I change the sign of the exponent, we keep the base the same, then that converts it from one of these to one of those, or vice versa. So exponential decay happens when I have x up here and this is less than 1, or if this is greater than 1 and that's a negative x, that's exponential decay. All right. Now exponential decay is not quite as common as exponential growth. You even see exponential growth in the way companies can grow. If a new company enters a market that no one else has competed in, the company tends to grow exponentially. Of course, it doesn't take long before other people see how much money these people are making, and they jump into the market. But before that happens, companies tend to grow exponentially. So, but how about decay? What decays? Well, companies can experience exponential decay too as their markets fall off. But normally you see this in more natural processes. Radioactive elements decay in terms of their original element. So for example, if you had a pound of plutonium, plutonium is what we dropped over Nagasaki, Japan to finally end the World War II. Plutonium is a very heavy element. It's artificially produced in reactors, and it only took a ball maybe this size that was imploded over Nagasaki, Japan, that was able to start a chain reaction that created this terrible nuclear explosion, which destroyed the city. Plutonium is a radioactive element, and we say it has a half-life, I believe it's 84 years. That means if you have a pound today, 84 years from now you'll have a half a pound of plutonium. Another 84 years you would then have 1/4 of a pound. And so it decays. Now where did it go? Well, that half a pound it loses over the first 84 years turned into radioactive energy, and it also turned into other kinds of elements. So but that's one place where we see exponential decay. And it's useful for measuring how old a fossil is. We use carbon-14 dating to date fossils, and this will be a very long video if I tell you about everything. But but one other example, exponential decay in electronics. If you know what a capacitor is, a capacitor stores electricity and it gets charged up, and then at some point you discharge electricity. So if you study electronics, you learn that capacitors discharge electricity according to this curve, and so you would have to know how to compute with that. If you pluck a string on an instrument, it eventually quits vibrating, and the rate at which it's vibrating falls off according to an exponential decay also. So it's it shows up. It shows up in various kinds of natural processes. Let me close out this this video by saying there's one, I can't remember who said this. It was a kind of a semi-famous person, and I thought it was kind of exaggerated, but he had a kind of funny saying. He said, the principal reason we have problems in this world is because the inability of humankind to understand exponential growth. And so I'll leave you with that. How many people understand exponential growth or can feel it coming? And I don't know. Maybe there's a little bit of something to that crazy saying. All right. Well, from here we're going to graph a couple of these and explore these, and so we'll go from there.